Hi guys, I'm back. I know I promised a video on the second video on our series, but I realized and remembered I wanted to do a little something dealing with meter loading. Now, what's meter loading? Well, for any meter, and whether it's your, say, your digital meter, sorry about that, such as this, when you check voltage in a circuit or current or anything, it takes a certain power, it takes a certain amount of the power from that circuit to operate the meter. Now, what does that mean? I have to take something from the circuit. If I'm measuring voltage, I have to take at least a little bit of that voltage to get this thing to read, to do something. Now, these are digital, and they don't take a lot. Basically, the way these are set up, and I want to show you some other little tidbits of information about these, but the way these set up are, they're basically an input impedance of around 10 megs. In other words, when you're measuring voltage, it looks like across the leads to the circuit that this is like a 10 meg resistor. If you got a VTVM and it's actually set up right, a lot of them has a, in the probe will have a 1 meg ohm resistor for DC measurements. But if you have a VTVM and it's set up with the proper probes and everything, or it's built into it, when you're doing DC voltages, it'll be actually 11 meg ohms impedance. Now, the interesting thing is, on digital meters like this one, this is auto ranging, but I can also set the range so it goes through the various ranges. Depending on what I'm measuring and what range it assumes to be in, it'll actually change its input impedance until it comes down to 10 megs. But it may start out as high as 11 or so, whereas a VTVM will actually stay steady. Now, there are other meters that were made besides digital and VTVM that are called VOMs. Here's an example, a Simpson. I have a Heathkit over here too that's the same way, same design. These do not take power to operate the meter as far as doing voltage. The only power they have in them is a battery or a couple batteries, and that's only for the ohm scale. But as far as the voltage scale and amperage scale, they derive their power from the basic circuit. Whereas the VTVM is actually, it does take some power from the circuit, but it also operates off of electricity to operate tubes in it that work a little differently. These here, this one here, I believe, yeah, it says right here. This one here, and if you can read it, I'll try to bring in, it says it's 20,000 ohms DC, ohms per volt. On AC, it's 1,000 ohms per volt. Now, what that means is, depending on what scale I set it on, if I set it on the 10 volt scale, at full scale, it's 20,000 ohms per volt. It's 20,000 times 10. That will be its input impedance or input resistance to the circuit. That's how much it's going to load the circuit. So 20,000 times 10 is 200,000 ohms. Whereas this meter if I'm looking at 10 volts as full scale or whatever, it's always going to be 10 megs. So it don't draw near as much juice. That's what meter loading's all about. This guy will draw a lot more juice than the other one will. And as well as my Heathkit, it's also 20,000 ohms per volt. So we did a little math, did a little circuit here. I won't really just write the math down. It's real simple math. I'll kind of go through what the math pertains. But we have a little circuit here. We have a 10 volt supply. It can be AC or DC. It doesn't make too much difference. Well, it does on these meters. If I was doing AC, this says 1000 ohms, so then things would be different. So we'll just assume that this is DC for placement of figuring out everything. So anyway, I got a simple circuit, 10 volt, say battery or 10 volt DC source going through a 100K resistor and a 1 meg ohm resistor. I'm curious about the voltage drop across the 1 meg. Now if I just do math and figure this up with Ohm's law, I end up with a total current of 9.1 microamps in the circuit and a voltage drop of across this 1 meg of 9.1 volts. Now what if I hook this meter here? It's 10 megs. If I hook him in there, now I'm adding a 10 meg resistor in parallel with the 1 meg. This is where I'm going to measure my voltage across. And what that works out to be, first of all, we got two resistors in parallel. Alright. When you do resistors in parallel, the actual basic math for it, there's a couple different ways of doing it. One is the reciprocal of the sum of reciprocals, and basically what that means is you take your R total will equal 1 over R, 1 over R1 plus 1 over R2, and then just plus dot 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 to whatever your last resistor is, however many resistors you want. In this case we got two resistors, so we just have just this. Now that's the reciprocal of the sum of reciprocals. And what you'd actually do, you'd put 1 meg here and 10 megs here and just do the math. Take the reciprocal of each one, add them together, and then take that reciprocal, and that gives you the total. Another way, when you have two resistors, of doing it is you can actually take R total will equal R1 times R2 over R1 plus R2. If you just got two resistors, you can do that way. Excuse me. In either case, it works out when I do the parallel of these two, since they're in parallel, it comes out to 909090.9 ohms, or rounding off 910K instead of 1 meg. What is actually effective resistance here now is 910,000 ohms instead of 1 million ohms. And then basically you figure out the circuit again, and when you do, making use of the new resistance that you have in there, you'll come out, instead of 9.1 microamps, you come out to 9.9 microamps, and the voltage will be equal to 9 volts. So this meter is going to see 9 volts instead of 9.1. Close enough for the most part. But if this was quite a bit larger resistance, say it was like 10 megs, then it would start making a difference, because if it was around 10 megs, the effective resistance would be quite a bit lower, and about half that, and you would have, it would reduce it tremendously, and our circuit would show up a lot different voltage than what is showing here. So that's what meter loading is. What meter loading basically is doing, it takes a certain amount of current from the circuit to drive the meter. Now, as long as the meter's resistance or impedance is large enough, and considerably larger, about at least 10 times larger, then it's not really that big of a deal. But if you get that a lot closer, or if whatever circuit you're measuring or whatever resistor you're measuring or that's in that circuit, if it's a lot closer to your meter in size or bigger, then your meter's not going to read correctly, because it's going to load down quite a bit of the current that would normally be going through that resistor. So it changes the total current in the circuit, it changes everything that's going on, and your voltage will be different, what you're measuring. Now, let's look at another circuit. Same circuit, but this time we're going to look at something like this one, except actually it wasn't this one. I've got a Heath kit over here, and it jumps from 5 volts to 50 volts, so I had to use the 50 volt scale figuring. Well, at 20,000 ohms per volt on the 50 volt scale, I get 1 meg total impedance, or total resistance in the meter. So I used 1 meg. When I work out this problem, these two in parallel come out half, 500K effective resistance. When I figure that in, my current now is, let's see, about 17 microamps. Quite a bit more draw current. The voltage that that meter is going to read will equal 8.3 volts. Drastically different. It should be 9.1. If I use that Heath kit on 50 volt scale, or if I use this one on its 50 volt scale, I would read 8.3 volts instead of the proper 9.1. That's when we're starting to really get serious meter loading. And it is actually loading it. What it's reading, it's not the meter's off. It's just the fact that it actually has changed that voltage drop, because it's drawing so much more current through the circuit and from the source, excuse me, that now that voltage drop on that resistor is now only 8.3. If I would take that down to what was on this one, to its lower level of 10 volts, because I got a 10 volt source here, so I should be able to measure that 10 volts there or less, then it'd be 10 volts times, remember it's 20,000 ohms per volt, so I'd take 10 times that, that's only 200,000. Then I'd have a 200,000 ohm resistor in there in parallel with 1 meg, so the total resistance is going to be less than 200,000. It's going to draw a lot more current. This voltage is going to drop even drastic more, and we will have even more being off of what it really should be. So if we do the actual math on that, then all we got to do is we look at, instead of having a 1 meg there, we have a 200K, so we do the parallel on that. Let's see, 200,000 plus, take the inverse of that, a 1 meg. We have an effective resistance now of 167,000. So if we take 167K, add the 100K to it, so So I take 167000. Oh, let's see. Gives me 267,000. Take 10. Divide by that. And that gives me about 37.5 microamps. If I take that current and then start and put it through our new resistance here, our new effective resistor here, so I take that times the 167, that gives me a V voltage drop of 6.25. And that's your meter loading. That's the worst case scenario. That's using this on the 10 volt scale in this circuit where I got 100K and a 1 meg. What it mathematically works out to be 9.1 volts. Using that meter and measuring it, I get 6.25 volts. If I use that meter or the Heathkit meter at the 50 volt scale, I get 8.3 volts, because again, it's 20,000 ohms per volt, so the higher the scale setting, you take that times that 20,000 ohms, and that'll be your input resistance into the meter. If I use my digital meter at 10 megs, it's 9 volts. If I use a VTVM, it works out to 9.02 volts. It's about as close as I'm going to get. But that's what meter loading is. So when you're checking a circuit, be aware of the load that you're checking across. It'll be primarily just that load. So if you're trying to measure in a circuit some very large resistor and the voltage drop across it, then be aware that your voltage that you measure may be off, or it definitely will be off. In fact, the closer that gets to the size of your meter's input impedance, the more it gets off. And when it is actually larger than input impedance, such as here, it gets way off. So just making you aware of it. In this case right here, this case is with a lot lower resistance, input impedance of 167K at 10 volts. This one here at 1 meg is with the 50 volt scale on a 20,000 ohms per volt meter. It gave me 8.3 volts. The 10 meg on the digital, 9 volts. Our actual voltage should be 9.1. If I use the VTVM, I'll get 9.02. So that's about as close as I'm probably ever going to get. Unless I use a scope. A scope's got considerably much higher input impedance. And depending on the scope, but it can be from 50 meg ohms to 100 meg ohms input impedance on the probe going into the scope or its inputs. So then you get a heck of a lot closer. You get almost dead accurate on a circuit like this. But I just wanted to make you aware of this. It does happen. So it does make a little bit of difference. Most of your schematics that you look at on these old radios and stuff, most of the time they were using, when they did the wrote out the voltages and stuff, it was figured using 20,000 ohms. In the later years, 20,000 ohms per volt meters, that would be most likely pretty much anything post-war, at least by the 50s. Probably a good possibility just right after World War II, and possibly during World War II, it could have been 10,000 ohms per volt. And very close, the late 30s, very early 40s could have been 10,000 ohms per volt. So it had been half this. And then if you go back in the mid 30s and early 30s, it was even half to even more. It could have been anywhere from 5,000 ohms per volt down to even 1,000 ohms per volt. Again, all that means is per volt. So whatever scale you're on, you take that times that, and that gives you the total resistance. So if I take it, I'm on a 10 volt scale, 20,000 ohms per volt, then that's got an input impedance of 200,000. 20,000 times 10, and so on. Excuse me. But just be aware of that. But most of those voltages that are wrote in schematics generally were done with either 20,000 or 10,000 or less. They used these when they did those. And so always be kind of aware of that too. And a lot of your good schematics will actually tell you what they used, especially Sam's, but some of the writers did too. To just kind of, so you knew heads up. So then on those, if you're using something like this or a VTVM, which are, the two are very close, then in cases like that, your voltage may actually be higher than what they're showing. So just realize that what kind of meters was used. The meters do load because they are drawing some current to operate them, and that depending on what kind of meter it is will depend on how much loading it is. Well, then we'll also then determine what the voltage in the voltage charts might have been and what you actually read. So most of the time the standard procedure is give or take, plus or minus 20%, because they don't know what kind of meter you're using. So most schematics, like Sam's, always said plus or minus 20%, because you may be using a VTVM versus they used a VOM, and they'll tell you what it is. They'll tell you that, and most of theirs I think were 20,000 ohms per volt. So anyway, that's what meter loading is. It can get to be something of a problem child depending on what you're measuring, so always be aware of it. That's how come I tend to use most of the time something like this or a VTVM, because those two have the highest input impedance, so they don't load the circuit near as much. But even then, if I know I'm going to be measuring something that's considerably across the resistor, it's considerably larger, like a 10 meg or something, then I go to the scope and I'll just do the reading from the scope. So anyway, that's about all I got to say on this. I will get to the transformers part 2 right after this video. I don't know what order they're going to be uploaded in, but this will probably get uploaded before the second part of Transformers. So anyway, until next time, thanks for watching. See you on the next video.